Hello, welcome back. In the last class we have discussed briefly about first order PDE, a bit of classification followed by Lagrange's method, how to get analytical solution, and we try to understand a bit of characteristics. What do you mean by characteristic curves? Okay. So, the solution of the PDE represents a surface. Okay. So, now let us proceed to second order, bit of analytical touch. So, then we proceed to the numerical methods. Okay. So, let us start with the second order. Okay. So, more general represents so u is our dependent variable. Okay, u is our dependent variable and x, y are independent variables. R, S, T are continuous functions of x and y, and g is in this form. So, definitely this can be considered as semi-linear. Okay. So, what do you mean by solution of this? Solution of this means any u which is u of x, y must satisfy 1. Okay. So, for example, consider for this u equals to f of x plus t is a solution because it satisfies this equation. Okay. So, now we would like to classify classification of second order PDE. Okay. So, let us consider 1 in the operator form where L is given by okay. So, I would like to draw your attention, some books put a 2 there, but I am considering just S instead of 2S. So, accordingly things would change a bit. So, now what do you mean by classification, and then how do we get the solution once we classify? See, if you look at this as such from the way it appears, it would be very difficult to guess what could be the solution. Okay. See, let us for example suppose something like this. So, it is very difficult to guess what could be the solution. Okay. So, somehow if we can simplify, see, look at the combinations, you have uxx, uxy, uyy. Okay. So, what would be our aim? Our aim is somehow transform 1 using new variables such that one takes a simple form. Okay. So now when we say what could be the simple form? Simple form such that this can be integrated easily. I mean, this is in a crude sense. Okay. So how do we do it? Okay. So what is our aim? Somehow transform one using new variables such that one takes a simple form. Okay. So let us try to introduce. Okay. Introduce independent variables x, y to zeta, eta such that zeta is function of x, y. Okay. So now our aim is to simplify the equation in terms of these new variables. Okay. So how do we proceed? So zeta is zeta of x, y. Eta is eta of x, y. So now ux, u zeta, zeta x. So we are using chain rule. Similarly uy, and the mixed terms say uxy. So this with respect to y. So we have here u z zeta. Okay, one zeta x is present and we are differentiating with respect to y. So we get this plus u zeta eta plus keeping this derivative of this with respect to y, then this term u eta zeta eta x zeta y plus u eta 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 x eta y plus u eta eta xy. Okay. So we similarly uxx. So for example, I can do then uyy, I can leave it. So this u zeta 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 x square plus so we make mistake, there is a chance. So first term u zeta zeta and this we get a zeta term plus u zeta eta, then keeping u zeta fixed. Similarly u eta zeta plus okay. So I will say, so these are some just two. Okay. So I am leaving u yy as exercise. Okay, that means u yy. So 2 in 1 reduces u, so r u x t, so this okay, only the left hand side I am considering. So it's a bit of algebra. Okay, so this say this plus g uy equals to 0 implies this plus some function we get okay equals to 0. Okay, so now this I will say 3. So this can be put it in a simpler form. You identify this structure. Okay, try to identify this. So 3 can be expressed as a times this plus 2b b of okay plus how did we do this? Look, so this I am putting it as a of, and this is same operator because r s t on this, so the operator is same, just here zeta x zeta y, eta x eta y, so this must be okay. So it can be put it in this form where okay and b so this is r s by 2 I would use, so 2 I would like to remove, t okay. So now an exercise a on this minus b square is 4rt minus s square so this exercise, okay, I would expect that this can be done. Okay. So now what is our aim? See, look at this 4. So in the new variables, our equation reduced to this. Now the question is, can we choose zeta and eta such that this takes simple form? What kind of simple form? For example, can we get zeta and eta such that, for example, this vanishes, so that we get u zeta eta, or for example this vanishes so that this form, etc. Okay. So what was our to choose zeta and eta so that 4 takes a simple form. Okay, what is this simple form? Say equal something, etc. Okay, so this is our aim. Okay, so this is our aim. Okay, so let us try to do that. Okay, so let zeta of c1 and eta of xy equals to c2. So then we have and so if this is the case, we have this. Okay, we get this we can verify if just by chain rule. Okay, just by chain rule. Then from these two, say this is some alpha. Okay, alpha, coefficient of u zeta in 4. What is our 4? This is our 4. So coefficient of u zeta is this. Okay, so this will be 0, implies R S plus T equals to 0. So please follow. Coefficient of this, which is this, so I am equating to with 0, so I have normalized by zeta y, so then it will be this, but from this we have dy by dx. This ratio is minus dy by dx. Okay, so this implies we have r minus b, sorry, minus s t equals to 0. This implies dy by dx equals to s plus or minus root s squared minus 4 rt by 2. Okay. So this is the scenario. Dy by dx is this. Okay. So that means if the coefficient of this in 4, okay, if this is 0, okay, so this will be 0, then dy by dx is this. Okay, right? So in some sense, if f of xy equals to c1 and f2 of xy equals to c2 are solutions of dy by dx plus lambda 1 xy equals to 0, dy by dx plus lambda 2 xy equals to 0, then zeta equals to f1 of xy, eta equals to f2 of xy are suitable choices such that eta y. Okay, see, we are forcing the coefficient of, I will explain. So coefficient of this is this. So we expect that this must reduce to a simple form. Which one? So for example, coefficient of this we want to be killed so that we get a nice form and it can be integrated very easily. Okay, so in order to do that, okay, so for example, we have considered these are constant surfaces, then from this we get this relation. So now if we force coefficient of this is 0, exactly we need this quadratic, and on solving we get dy by dx. Okay, so this is say lambda 1 lambda 2. Okay, so essentially that's what we get. Dy by dx plus lambda 1 is 0, dy by dx plus lambda 2 equal to 0. So then zeta equals to f1 and eta equal to f2 are suitable choices such that, okay, see, only this happens, then the coefficient will become 0. Only this happens, the coefficient will be 0, and only this happens, the coefficient of u eta will be 0. Okay. So these choices make okay. So these choices will make these coefficients 0. Okay. Hence 4 reduces to some phi of okay. So, this we can easily integrate. So, the curves so these are called characteristic curves of 1. So, these are nothing but carriers of discontinuities, because how did we along this the coefficient is getting 0. Okay, that is how we have determined. Okay. So, these are called characteristic curves. So, now this depends on how many characteristic curves exist, depends on this quantity. Okay. So, various possible cases we can discuss. So, for example, if this is positive, then we will have 2 distinct, and if it is 0, then we have only 1. If it is negative, then we have imaginary, right. So, we are going to discuss. Okay. So, case 1, s squared minus 4 odd t greater than 0. So, if this is the case, then r alpha squared plus s alpha plus t equals to 0 has 2 distinct real roots, lambda 1 and lambda 2. So, therefore, we get dy by dx plus lambda 1 0 dx plus lambda 2 0, and on solving we get zeta equals to f1 of x y, eta equals to f2 of x y. Okay. Then case 2, s squared minus 4 odd t equals to 0, then roots are equal. Okay. So, that means in this case 2 real characteristics. Okay. So, roots are equal. So, then we have only zeta of x y, which is as solution of dy by dx plus lambda equals 0. Okay. So, which means we have one here, and then we have to choose eta equals to eta x y independent. Okay. So, we have to choose eta equals to. So, if this is the case, okay, So, in this case what would happen is we have a of zeta x zeta y 0, and since eta is independent of zeta is non-zero and b is 0 in this case. So, the equation 4 reduces to okay. So, this is case 2. Then case 3, s squared minus 4 r t is less than 0. So, this is more or less same as case 1, but roots are complex. Okay. So, we have to roots are complex. So, we cannot work with zeta and eta. Okay. So, here in this case these are complex, hence we define alpha equals to half of zeta, beta equals to, and try to change the entire equation in terms of alpha and beta. So, then 4 reduces to okay. So, what is the representation corresponding to each of the cases? S square minus 4 r t greater than 0, then the equation is called hyperbolic. Okay. Then s squared minus 4 r t equals to 0, parabolic. Elliptic. So, that is because when the transformed equation in the new variables almost represents a conic. So, these words are derived keeping the transformed equation in terms of a conic. Okay. So, examples. So, examples. So, this is Laplace equation. You can verify s square minus 4 r t less than 0. So, it is elliptic and so this is heat conduction equation, of course one dimensional. This is parabolic, and this is one dimensional wave equation, which is hyperbolic. Okay. So, these are I am not giving the derivations of these equations, but these are most physically discussed examples with respect to second order PDE. Okay. So, we have not seen the advantage of reducing it to new variables. Okay. So, let us see that. So, that is called canonical form. Which one? Using the new variable and reducing it to canonical form. So, let us see the example. Suppose this is our equation. So, here r is 1, s is 0, t is minus x square. So, s square minus 4 r t is 4 x square greater than 0. So, it is hyperbolic everywhere. So, now consider so this implies alpha square so let the roots lambda 1 is x and lambda 2 is minus x. So, dy by dx plus or minus x equals to 0. So, this implies y plus or minus x square by 2 is C1 or C2. So, therefore, zeta equals y plus x square by 2 and eta is y minus x square by 2. That means, for this choice of eta and zeta only, this equation gets reduced to a specific form. So, that is a idea. Okay. So, if you use the chain rule and try to reduce this, gets reduced to so which is a simpler than the original. Okay. So, let us consider another example. Looks big, but let us simplify. So, we get so this implies so lambda equals to x by y. Okay. So, dy by dx equals to minus x by y. So, zeta of x y, one characteristic. So, since roots are equal, what was our earlier discussion? Choose eta which is independent. So, let us choose. Okay. Then, if we use zeta this, eta this, okay, then our equation reduces to, so this is exercise please, using chain rule. Then what is advantage? So, this is our canonical form, and hence if you integrate and further if you integrate, which is nothing but so any combination of these functions will be solution of the original equation. Okay. So, this is reduction to canonical form, and once it is reduced to canonical form, solving. Okay. So, this is using a change of variables and reducing it to canonical form, so that it is easily integrable. Okay. So, now let us look at physically complete set of equations, each of the categories, for example, elliptic, hyperbolic and parabolic. As a physical problem, let us define, that means together with the boundary and initial conditions, so that we are making our setup to proceed to numerical computations. Okay. So, let us define the complete set of problem. Okay. So, let us start with heat conduction. So, in case of one dimensions conduction in of some length. So, I am not giving the derivation, as I mentioned, this is our equation. K is the constant of this is the thermal conductivity coefficient, and we are discussing within a specified length. So, now this requires what are the boundary conditions, and see, we are looking for u of x t. Okay. U of x t for t greater than 0 within this range. So, definitely we need a initial condition and then we need the boundary conditions. Okay. So, boundary conditions, we need u of, so let us say this is 0 and L, some t 0, u of 1 t, in this case L t, some T L, and we need an initial condition u of x 0 is any initial profile. Okay. So, this is heat conduction. So, remember I am putting down only one dimensional cases. So, in this case the solution represents the temperature for a given time at any point. Okay. So, that is the solution. So, now in this case wave equation. So, again it depends for t and x. So, which means both ends are fixed. So, what this represents, this equation governs the displacement of a string, in this case which is fixed at both ends. Okay. So, how it is getting displaced. Okay. So, as a set of physical problem, we need boundary conditions. Okay. So, what are the boundary conditions? Since both ends are fixed, so u represents displacement in this case. In the earlier problem, u represents temperature. In this case, u represents displacement. So, the boundary conditions, since both ends are fixed, we have no other option for all t. Okay. Then we need initial conditions. Remember, this is a problem on displacement and we have two time derivatives. So, we require initial displacement and velocity. So, this is the complete physical problem. Okay. So, now Laplace equation. So this is in two space dimensions. Okay. So now I would like to mention here, if u of x y equals to some f, okay, on the boundary. So this is called Dirichlet condition. Okay. Then Neumann condition, if the normal to the boundary is prescribed, of course on the boundary, then Robin condition, a scalar times u plus another scalar times normal. So this is prescribed, h given, all are given. H given on the boundary. Okay. So this is Robin condition. So before we go for numerics, let us see for the simple cases, can we get analytical solutions. So one, since the equations are linear, okay, so we would like to attempt separation of variables. So consider so k I have taken as 1. So now we have to define the complete problem. So initial condition and boundary condition, so since we would like to try a separation of variable solution, let okay, so then 1 implies we get lambda say. So by substituting this in 1, we get this. Okay. So independently we solve. Okay. So then applying boundary condition, okay, this implies u of x t okay. So then boundary condition implies lambda values are determined. Okay. So therefore this is the solution. Okay. Now we are still left with initial condition. Okay. Suppose, so we are left with f of x. Suppose f of x is x and 1 minus x, this range. Then how do we determine a? Okay. So what we do is we depend on the Fourier series of f. So, let the Fourier series of f be this, where a n okay. So, then we can employ the initial conditions, because see, look at it, we need f in this form, u in this form, but the initial profile is given in this form. So, we depend on the Fourier series and we employ the initial condition, so that we determine the coefficient a n's. So, therefore, u x t is given by okay, which is okay. So, we get the solution. So, initial condition is applied depending on the relying on the Fourier series of f. Okay. So, similarly, let us consider Laplace equation. So, now we need two conditions on x, two conditions on y. So, the entire boundary is prescribed. So, we follow the same procedure. So, this implies so, therefore, and again depending on the form of f, we determine a. Okay. Determine a using, of course, via okay. So, now where is the numerics, where is the necessity of numerics? Okay. See, we have got the solution very nicely, and then where is the question of numerics? The question of numerics arise, for example, if your boundary is not regular. Okay. So, using separation of variables we get it, but unfortunately to get the arbitrary coefficients, if your boundary is not regular, then we cannot really substitute and get the exact arbitrary coefficients. Okay. So, for example, we are solving Laplace equation and the boundary is something. Okay. Suppose on the just now we have solved on a square. Suppose there is an extension given. So, this is our new boundary. Okay. So, suppose from here to here u is 1 and here u is 0. So, how do we solve? Because our solution we cannot represent using one single, because our solution is okay. So, it consists of like this e power root these terms product with so this line can be represented using the Cartesian coordinates, but there is no single equation. Okay. So, we will end up with the difficulties. Okay. So, in order to solve such irregular geometries, even though equation is linear, in order to solve such irregular geometries, we have to go for numerics. Okay. So, with this motivation, in the coming lectures we start numerical methods for partial differential equations. Until then, goodbye.